So everybody get up. We're going to do some exercises. No, just joking. So thank you, organizers, a lot for this amazing event, both emotionally and scientifically. And in particular, thank you for placing me after Sylvia's talk, which in my mind is probably only competed by Noam's task of speaking after Inat's amazing talk today. So I want to tell you a little bit about how it started between me and Avi. I don't know if you remember Avi. Radisson Hotel, Burlington, Vermont, 96. I was by then in a superposition of advised by Noam and Michael Ben-Or, and Noam was slowly stepping out of theory, and I was thinking to myself, what should I do? And while I was walking in those corridors, you can look for Avi's hidden there. While I was walking there, I was sort of thinking to myself, what should I do? And I was also thinking about my talk, my first ever Fox talk, and I encountered Avi surrounded by about 10 students as usual, or colleagues. And so the conversation went something like this. I came to Avi, I said, I want to do a PhD. Avi said, great. With you. Great. And that was it. That's how we always understood each other with very few words. And then I recalled that I forgot something very important to say. I started walking away thinking about my talk, but I recalled that I forgot something very important. So I turned around and I called Avi and I said, it's because I love mathematics. And Avi shouted above the heads of these 10 people, me too! So Avi loves mathematics. And so he loves, I think the thing, correct me if I'm wrong, but I think the thing that you really love is interesting connections and surprising and sort of unexpected connections between different things. Now, trying to compete with Silvio, I thought that, well, night is really great, but being a Buddha is something slightly above it. So Avi really touches with his hands essentially all of theoretical computer science. And I think that Avi's most passionate thing is trying to embed all these ideas in various different areas, all these beautiful fundamental ideas like hardness and reductions and interaction, etc. And so Noam talked today about the computational lens. And this is a particular passion of Avi of introducing these ideas in other areas. And so today I want to tell you in this talk about something which goes along these computational lens idea of introducing theoretical computer science to other sciences. So this is a continuation sort of computational economics, computational biology. And what I want to tell you about today is a very exciting progress in my mind in the past 10 years, past decade, in which these wonderful ideas are starting to penetrate physics. And I'm not talking about just starting to penetrate physics in the terms of asking whether a quantum computer will be built, but actually penetrating the very core study of physical systems. Okay, so Avi always talks on the phone in these pictures. So I'm going to, I picked three particularly nice connections that I found, but there are many others that have been penetrating physics that we won't talk about. So the first one is how NP is somehow insightful, telling us things about quantum states. The other thing is interactive proofs. And somehow they have amazing insights about how can we do experiments. And the third thing is a very surprising and intriguing connection that has been formed over the past few years, in which those ideas of theoretical computer science enter quantum gravity. And so I won't have time to tell you about quantum gravity a lot, but I'll just mention how error correction gets into the picture. Okay, so I want to start setting the grounds for this. And I want to start with here at Princeton. So this is John where are we? Okay, so this is John Conway's beautiful model of game of life. And I think this is perhaps the most beautiful demonstration of how simple rules accumulate to bring up complexity. So probably you all know this model. You have some initial configuration of this cells, and then they are predated by very simple local rules. And from these accumulation of local steps, you get full complexity, you get universality. And these type of update rules, or this type of how complexity is accumulated, also appears in essentially any computational model that we can think of, like Turing machine, like the circuit model, like DNA-based computation, and like even computations based on chaos, if you really make sure that the precision, that you're not assuming infinite precision or anything. And this is captured very nicely by the extended Church-Turing thesis, which states that any computational model can be simulated efficiently by the Turing machine. Efficiently meaning in polynomial time, polynomial overhead. So the real essence of this is that basically information processing in the classical world is done, whatever computational model you can think of, it's done all in the same way. You have classical strings and they're updated by local rules. Quantum information is slightly different. So here's a crash course in quantum information. They don't work with classical bit strings, they work in superposition of classical bit strings. So n quantum bits, qubits, can live in linear combination of these n bit strings. There are 2 to the n bit strings, so a general quantum state will be in a linear combination of these n bit strings, of these 2 to the n bit strings. And you have, where is it? So you have these coefficients which can be complex. You can think of them as can be real, and in general you need 2 to the n real numbers to describe such a state. Now it's very nice to think, it's very beneficial to think of the analogy between this state and a probability distribution over n-bit strings. And the point is that if you can measure this state and get a string I with probability ai squared, which is why this equation needs to be to hold. But these quantum probability distribution behave very differently because they somehow, if you measure this state in a different way with different bases, you get stronger correlations. You get very weird correlations, which are called quantum entanglement. And this quantum entanglement buzzword, we'll get to it. Okay, now how do you define okay, so in order to talk about how information is being processed, you also need to talk about dynamics. And you define a quantum time evolution in a computation in the same way that the classical computation works. You have an initial state, you have some simple dynamics consisting of elementary steps, and then you measure, or you look at the output. And Schrödinger's equation tells us, quantum mechanics tells us that the evolution is governed by Schrödinger's equation. And Schrödinger's equation here is written as the derivative in time of the state, the quantum state, is equal to some operator, which we'll see later, the Hamiltonian applied on the state. This Hamiltonian is a 2 to the n by 2 to the n matrix. It's a huge matrix. And it tells us how the state evolves in time. And if you integrate this equation, you get the famous unitary evolution, the discrete unitary evolution of the state. Now, not all Hamiltonians are equal. I mean, physics doesn't allow us to apply any general Hamiltonian. Can I apply this? Can I do this? No. Actually, you're only allowed to apply, simple Hamiltonians. In particular, local Hamiltonians. So a local Hamiltonian here would be a sum of local terms, where each term acts on a small number of qubits. Okay, so without getting too much into the details, what this means is that the unitaries that we're talking about, evolving the state, have to be composed of small elementary steps. Okay, so here's an example of a quantum gate, a very simple quantum gate acting on one qubit, one quantum bit, and it just takes a 0 to 1 and 1 to 0. And if it acts on a superposition of strings, it flips the bit in each one of the strings. Here's another classical gate. This is a classical gate because it just permutes the bit strings. Here's another classical gate. And in fact, the only thing you need to do in order to add something to classical computation, in order to get quantum computation, is to add one single extra gate, which is called the Hadamard gate. And the Hadamard gate is the gate that takes 0 to 0 plus 1 and 1 to 0 minus 1. You would notice that it takes a state to a superposition of states. And it turns out that this is sufficient to get quantum universality. So Avi asked yesterday, or 2 days ago, why do we only see quantum algorithms which use Fourier transforms? In fact, this is a partial answer. Because Hadamard is a quantum Fourier transform, and it suffices to add Fourier transform and to classical computation to get everything. But Avi is doing this. No, you can ask now.
Well, the quantum Fourier transform is applying 1, 2 to the n by 2 to the n matrix, of course, composed of these kind of things, but in a very specific way.
Right. Yeah. So as I said, it's a partial answer. And really, of course, this is an assembly answer. And what you really want is you want a combination of techniques that in a higher resolution that will use these ideas. Anyway, complexity here is measured by the number of gates. And that's a quantum algorithm. That's a quantum computation. That's how quantum information is processed. Okay, so what is so special about this information processing in a quantum system? Well, it turns out, and probably the best example, as I'm sure you've all heard, is Shor's algorithm. Turns out that this additional power of the Hadamard gate, or allowing such superpositions, enables a quantum computer to factorize numbers, which is an exponential speedup, as far as we know, as far as we guess, over any known classical algorithm. Now, there are other quantum algorithms which do use completely different techniques. One of them, for example, is an approximation quantum algorithm for knot invariance. And the other is some graph reachability algorithm in a highly symmetric graph. And the techniques there are very different, but admittedly, these algorithms are highly specific, and these techniques have not succeeded to sort of be applied in a wide range of problems. Shor's technique, however, is surprisingly applicable in many, many different directions. And there is, for example, Haro-Hasidim-Lloyd algorithm for linear equations, for solving linear equations exponentially faster than classical computers if the set of equations is given implicitly. Some extension of Shor's algorithm to some number theory question of computing the unit group in a number field, and so on. So I'm not going to tell you anything about how these algorithms work. But I do want to say something that hopefully will take the mask a little bit of this word of entanglement, which is a buzzword that people have been throwing everywhere. So 3 examples of entanglement. Okay, so the first example is Bell's inequalities. Here's a computer science way of looking at Bell's inequalities. Actually, I'm not going to go into the details of that because I assume that many of you have sort of heard this thing. But the idea is that in Bell's inequalities, or in the computer science version, which is a game, Alice and Bob play against the referee, and they want to win in some way. And they want to win against the referee. And the game is that they are allowed to meet beforehand and talk between themselves, but after they meet and talk, they are separated, they're not allowed to communicate, and then they get some question from the referee, some random bit, and then they need to answer a random bit. And they win according to some rules, and the point is that each of them doesn't see the other person's bit, so they cannot correlate to the other person's input, but the rules are correlated. So here are the rules. They're not important for now, but the point is that it's very easy to prove that they can win only with probability 0.75, no matter what they do, classically. Quantumly, it turns out that if they share a quantum state, that's called an EPR state, which is an entangled state, they can somehow manipulate their measurements, rotate their measurements based on their own inputs, such that their correlation is larger. And without exactly explaining how, well, what that means is that quantum correlations are actually stronger than anything explained by classical physics. And this can actually be performed in the lab, an experiment like that. Alana Specht did this experiment in the 80s. And this can be viewed as a test for the fact that entanglement or quantum correlations exist in nature. So that's for two particle correlations, two particle entanglement. One particle entangled to a larger system is something that maybe less people here saw. So here is a classical task. Okay, so you're given, so now think classically for a moment. Here's a problem. You're given access to two boxes. One box contains some samples from some distribution, P, and the other from a distribution Q, and you can query and get one sample from either one of these distributions. And you're promised that either the distributions are exactly the same or they're non-intersecting. And you want to distinguish between the two cases, and that's the only thing you know. How many samples would you need in order to do that? Avi. N-bit strings. 2 to the n over 2. Well, there's the birthday paradox, but still, you need exponential. You basically need to sample until you see collisions, and that takes exponential time. Now, if you have a quantum sample, that's a completely different thing. Suppose you're given a state which is a superposition, which is the quantum analog of this probability distribution. You can, of course, do the same thing classically. You measure, and you get the samples, and you do the same thing. But you can be more clever and use entanglement. And here's how this is done. You can actually, well, in order to decide whether the two distributions are the same or non-intersecting, you need to decide whether P and Q are orthogonal or the same state. And to decide this, well, you can do this. You can entangle these states P and Q to an additional extra 1 bit, 1 quantum bit. 0 is entangled to P, 1 is entangled to Q. And if you can generate this state and apply a Hadamard, here's the Hadamard in case you forgot, well, 0 goes to 0 plus 1, 1 goes to 0 minus 1. And what happens is that if P and Q are the same, these two cancel out. This is interference. And so if you measure the control bit, you'll find only 0. So that means that, well, you'll know from the control bit whether P and Q are orthogonal or not, because if they're not the same state, you will have a probability half to measure 0 and a probability half to measure 1. More generally, the probability for 0 depends very nicely on the inner product. That's a simple calculation. So by entanglement between one qubit and as large a system as you want, you can gain information about the inner products of the state of the large system. Okay, so that's about entanglement between a qubit and a large system. Now, what about entanglement between many particles? And so I think the most beautiful example of this is what's called quantum error correcting codes. And in particular, a very beautiful example by Kitaev, the toric code. And so, okay, so imagine that you have on each edge here a qubit in the middle of the edge. And I'm going to construct a state that will have multi-particle entanglement with very beautiful properties, topologically related properties. The way to construct such a state is by, again, using this Hamiltonian, but now I'm not going to refer to this Hamiltonian as really something that corresponds to the dynamics of the system, but instead I want to refer to this Hamiltonian as a 2 to the n by 2 to the n matrix, which has eigenstates. And in particular, I'm interested in the lowest eigenstates of this matrix, the ones with the lowest energy, which are called ground states. Kitaev constructed the following Hamiltonian. It's a local Hamiltonian. So each term is local. It acts on 4 qubits. And there are 2 types. For each plaquette, for each square here, there is a term that acts on 4 qubits, and it performs some projection. Okay, the Hamiltonian will be viewed as some projection, or in other words, a constraint on those 4 qubits. It's a projection, so if the eigenvalue is 0, then we will say the state satisfies the constraints, and otherwise it gets an energy penalty and it does not satisfy the constraint. And the constraints written by these Hamiltonians are as follows. If you have, well, for a vertex, the constraint would be in the computational basis, and the constraint is that for those particular 4 bits, the number of ones need to be even. So if a string satisfies all constraints of this vertex type, what kind of a string is it? Huh? Nati, you should. Union of cycles, exactly. And okay, that was a question for Nati Lanchata. Okay, and then for this type of constraints, you have the same idea, except it works in the other basis, in the Hadamard base, in the plus-minus basis. And again, this requires, the constraint is that the number of pluses here is even. So never mind exactly the details, but the point is that these constraints somehow commute, and it is possible to satisfy all constraints. And in fact, there is a subspace of dimension 4 that satisfies all constraints. And this subspace has very beautiful properties. In particular, it is all states in the subspace are highly entangled. How do you see this entanglement? Well, here's one way. Suppose you flip the bits along this simply connected loop. It turns out that for any state in that subspace, the state doesn't change. Now, already this is a bit surprising, because if you have a bit string and you flip bits in it, it changes. But if you have a superposition, it can be invariant to a change. But this is nothing. The next thing is much more interesting. Suppose now that instead of the loop being simply connected, you flip the bits along a non-trivial loop, wrapping around the torus. Well, what happens here is that this flip will actually change the state. So the states somehow encode the global information about the torus, topological information about the torus. And even though they satisfy local constraints. And these 4 states, remember I told you that there are 4, it's a 4-dimensional subspace. This corresponds to the fundamental group. This corresponds to this wrapping around the torus, to a trivial loop, to a wrapping around the torus this way, or both of them together. And it's even more than that. The point is that this information is encoded in this global state, globally, and it cannot be accessed locally. If you just look at the qubits in such a state, and you just look at a small number of qubits, which sort of is not enough to wrap around the torus, like a small patch here or this patch, it will not distinguish between the different states. The states cannot be, if you perform any measurement on these states, you will not be able to distinguish between any of these 4 states. So in any state in the subspace. So the information is somehow spread on all the qubits, but locally it's not there. And this is what makes it possible to use those states for quantum error correcting code. Because if you think of the error as being local and as being a measurement that collapses the state, for example, well, if the information is spread globally and is not accessible locally, whatever you do locally to the state doesn't destroy it, and therefore you can correct it. So this is just 3 examples for what entanglement can look like. Okay, so to summarize this part, here is a computational language summary. We have P and BPP, which Avi will say that was a redundant picture. And we have BQP. BQP is the class of problems that can be solvable by a quantum computer in polynomial time, and these are the class of problems that can be solved in polynomial time by a classical computer. And we believe that BQP is strictly bigger than BPP. And so, because of factoring here. So this is a mathematical belief, right? It's a conjecture. But we also believe a speculation that, well, we is, by the way, quite ill-defined. Luckily, Gil is not here. We believe that we can actually implement BQP in the lab. And that's a physical speculation resting a lot on this quantum error correcting ability that somehow enables us to correct errors and not to require that the system is ideal. And these two together amount to the fact, to the belief, that quantum computation, if and when realized, will actually violate this extended Church-Turing thesis. It will correspond to a completely different type of information processing. Okay, so just to put things in context, NP is here. It's not in BQP. NP is this class of problems which can be, whose solution can be checked easily. And it's a class of very hard problems, and we don't believe that it's inside BQP, but we also don't believe that BQP is inside NP. And here is quantum NP, which actually contains NP and BQP. And these classes, I will explain a little bit what that is, but these classes, QNP and NP, are believed to be different. Okay, so here's the time for a silly question. Okay, so if you don't have the courage for a silly question now, let me inspire you by a story. Okay. It's both. I tried to be a little bit more clear than usually when people talk about this. There are 2 assumptions here. One is a mathematical conjecture, which is that the model BQP, which is well-defined mathematically, is different than BPP. And then there's another assumption that this model, BQP, can be realized in the real world. I wouldn't say, I mean, I'm not going to be, am I recorded? I would say that I don't very strongly believe either of these very strongly believe assumptions. I mean, I don't think that we've really tested all these 2 assumptions very strongly, but there are good reasons to believe both of them. Because the first one, BQP versus BPP, just seeing how information is processed, it seems highly unlikely that they will collapse somehow. I can tell you that I tried to collapse them for a long time. The fact that I didn't succeed doesn't say much. And about implementing, well, the threshold theorem and the error correction say that if our assumptions that errors are really local and somewhat independent to some extent, or weakly independent, then we know for sure mathematically that this can be done. But whether this assumption is correct or not, well, we have to wait whether people will actually be able to implement those computers. But we'll get back to this question in a little bit. Okay, so back to my story. Well, this wasn't a silly question, so that doesn't count. If you're having a hard time being encouraged or having the courage to ask a silly question, I find Avi's ability to ask silly questions very inspiring. And I would like to tell you a particularly inspiring point in my life when I was sitting with Avi at a colloquium of inertia Liv, and it was a colloquium about group theory. Mind you, that was after Avi told me he really likes mathematics. And we were sitting in this colloquium, and we heard this talk about groups and various blah, blah, blah. And after 15 minutes, Avi raises his hand and asks, "What's a group?" Anel actually answered. Do you remember this? No. Okay, of course you would.
Well, it was almost as serious.
No, actually, I have to admit, I changed the story. It was, what's a simple group?
Yes.
But, but that, you remember that. Okay. But allow me for your birthday to modify a little bit.
I didn't answer because he thought Avi was joking.
Okay, you remember that too? Okay, so any silly question? Okay, so now we're going to move forward in the absence of silly questions, Avi, to how this can be, how these ideas can be used in the context of understanding quantum systems, physical systems. Okay, so we'll start with NP and the complexity of ground states. Okay, so we don't understand quantum states. I gave you some examples about entanglement, but we really don't have a very good theory of quantum states. And what is it that we really want to do? Well, first of all, quantum states is huge. The Hilbert space is huge. It's 2 to the n dimension. Just an epsilon net is doubly exponential. Most states are just not even specifiable. We're interested in states that are interesting for physicists or that are reachable in polynomial time by quantum evolutions. So this is a very small subset of the Hilbert space. But okay, so let's concentrate on that. Say ground states of local Hamiltonians. What we would like to do is we'd like to have some kind of a roadmap of which states are easy and which states are hard. Right? As theoretical computer scientists, we would like to somehow say something about the complexity of those states. Easy states would be states that have simple classical efficient descriptions from which you can deduce anything you want classically. You can simulate them. And the other states, well, the other states are not. And how do you argue that a state does not have an easy description? So it turns out that for the easy part, there are lots of heuristics as well as lots of insights about how you can describe states with efficient descriptions by bounding the amount of entanglement. I'm not going to define the amount of entanglement. It's usually quantified by entropy. But there is this notion called an area law, which says that usually in typical physical systems, the amount of entanglement between two parts of the system A and B would be proportional to the area rather than to the number of particles on each part. And that basically corresponds to the amount of entanglement, the entanglement being confined to local interactions between the, close to the boundary.
So the area, you mean the boundary?
The area is the size of the boundary. Okay, so I'm not going to talk more about this because I want to talk about the computational hard part. And in order to argue that states are hard, we will need some kind of a computational hardness notion, and that will be quantum NP. How exactly you deduce from quantum NP completeness the hardness of expressing states, we'll get to that in 2 slides. So what's quantum NP? Well, okay. NP, you have a Boolean formula with local constraints. That's 3 sat. You want to know if all constraints are satisfiable by some assignment. And as we all know, well, you can do that if you get a hint, an assignment. But if you don't get a hint, it could be very difficult. So given the hint, it's very easy by some classical computation to verify that a formula is satisfiable. what would be the quantum analog of that? Well, the quantum analog of NP, the quantum analog of NP would be this creature here in which the input is classical, but everything else is quantum. The verifier is quantum, and the state, the hint, is a quantum state. Now, a fundamental theorem in NP theory is that this problem 3 set is not only in NP, doesn't only have a verifier that is easily checks whether the solution is correct or not, but it's also NP complete, meaning it can encode any NP problem. So is there a quantum analog of this? A quantum Cook-Levin theorem. So what's the quantum analog of SAT, and what's the quantum analog of Cook-Levin? So Avi, I don't know if you remember, you probably remember, but Avi is responsible essentially to the solution of this problem. And the reason is that in '98, I was talking to Avi and I told him, well, there's this amazing guy called Kitaev, and Avi said, well, let's invite him. He got on the plane from Russia. 2 days before he got on the plane, he was thinking to himself, I'm going to talk to Avi Wigderson, and I don't have anything to say to theoretical computer scientists. I'm a physicist. So 2 days before he went on the flight, he invented the quantum Cook-Levin theorem, which is by now actually the seed for the whole field of quantum Hamiltonian complexity. So how does it go? So what would be the analog of quantum of 3 set? The analog of 3 set, you've seen it already. You might be guessing. Here is 3 set or constraint satisfaction problem, and the analog of this turns out, this is probably the major problem in theoretical computer science. The analog of this turns out to be the major problem in condensed matter physics, which is finding the ground state of a local Hamiltonian. And the way to see that these two are connected is basically recalling that these elementary, these local terms in the Hamiltonian can be viewed as quantum constraints. So you can look at these constraints, and you can actually take a formula with local constraints and map it to a Hamiltonian acting on n qubits, where each constraint like that is mapped to a Hamiltonian which projects on everything violating this constraint. So this is actually a proof that computer science is all but a special case of condensed matter physics. And so, no, is there an objection?
That's the inverse.
The inverse is?
Condensed matter physics is a special case of computer science.
Yeah, but I just proved the opposite. So the reason why this is a subcase is because, well, this is a special case. This is a special case, but in the quantum case, you can have Hamiltonians which do not necessarily diagonalize on the computational basis. They don't necessarily commute. They can be general, and therefore, the ground state of these Hamiltonians need not be a computational basis state like it is in the classical case. It can be highly entangled. Okay, so it's rather, once you grasp the notions, it's not very difficult to see that this problem of estimating the ground value of a local Hamiltonian is inside quantum NP, the way I defined it by a quantum verifier and a quantum witness. Because if I want to estimate the ground value of a local Hamiltonian, what would be the natural witness? The ground state. The ground state would be the witness, and once I've given it, I can estimate the energy. The real problem is how you can actually prove that this state encodes, that this problem encodes somehow any problem in quantum NP. Okay, so this is the only technical slide in this talk. So, but it's a 2-minute slide, and it's not too technical, hopefully. So how does the proof go? So Kitaev showed that this problem is indeed complete for quantum NP, meaning any quantum NP problem that can be verified by a quantum verifier can be encoded into a local Hamiltonian. Well, to do this, recall how the classical Cook-Levin theorem works. It essentially just talks about the fact that computation is local. So what do you need to do in order to show that 3-sat is NP complete? You need to take a verification computation and encode it into a 3-sat formula. And the way this is done, well, you look at you sort of set up the computation evolving in time like this. And for any point here, you assign a variable. And the point is that since computation is local, the verification process is local, in order to make sure that the variables really encode a correct verification process, you just put local constraints. So, and this is how you get a 3-sat formula or a 6-sat formula, whatever. So you want to do the same thing quantumly. But now you encounter a problem. And the problem is entanglement. If you want to take a process, a quantum evolution process, and put constraints on the set of quantum states so that you make sure that the states evolve correctly, well, you can't do that because of what I told you before about the story code or multi-particle entangled states. States can be completely different, but look locally exactly the same. So you cannot have local constraints checking that the evolution is correct. So how do you combat this? Well, you combat this with another thing that I told you about before, which is you entangle the state to another small system. And then once these states are entangled to another small system, just like in these boxes of 2 distributions, now by projecting this extra system, you will be able to know what's the inner product between these 2 states, and make sure that it is either the same if the computation is trivial, or you do something when it's not. Okay, so this is how Kitaev managed to prove that quantum NP, that local Hamiltonian is really complete for quantum NP. So he actually constructed a local Hamiltonian, whose ground state is this correct history of evolution of the quantum verification process. Okay, forget the details. What we've shown now is that local Hamiltonian is quantum NP complete. How do I deduce from that what I wanted to deduce before, that there are quantum states which are hard to describe, or which do not have an efficient description? So this is very simple. Suppose a class of Hamiltonians is quantum NP complete. And suppose that any ground state has a classical efficient description. Well, this classical efficient description could be used as a witness. And then quantum NP would become NP. But they're 2 different classes, so that's impossible. So if you have a class which is quantum NP complete, it cannot be true that all states have efficient descriptions, because that would make it a classical NP. Okay, so this is a way to say that classical states don't have quantum states don't have efficient descriptions. It also says something about the exponential time it takes for the state to relax to its ground state. Because if for that ground state, for that particular Hamiltonian, the system, the problem is quantum NP hard, then it cannot relax very fast to its ground state, because that would make it solve a quantum NP hard problem.
That's
So
even for SAT, right? Even for like these quantum Hamiltonians.
That's true.
Corresponding to
That's
SAT.
true, right. Okay, so just to summarize this part, this actually leads to various understandings about Hamiltonians. For example, in one-dimensional systems, physicists, first of all, classical one-dimensional constraint systems are easy, dynamical programming. Quantumly, physicists use the heuristic called DMRG, which works all the time. But it turns out that if you work a little bit harder on Kitaev's reduction of any quantum NP problem to a local Hamiltonian, you can make that local Hamiltonian sit in a one-dimensional line. And that means that, that even 1D systems are quantum NP hard. So this is in strike contrast to classical systems which are in P. Okay, and this is even true for translation invariant systems. So even physically reasonable systems, translation invariant, one-dimensional, are quantum NP hard. And it's a very intriguing question to ask, what is the source of hardness here? What is it that makes these physical systems hard and other systems easy? Maybe it is robustness, I don't know. But these kind of arguments somehow create a roadmap on the set of Hamiltonians and allow us to do reductions between different classes of Hamiltonians and tell us when different Hamiltonians somehow have the same information content or complexity content, even though they look very different. And this has a lot of applications to other things, which I won't get into. I want to go to the other thing, the second thing, which personally I like very much, interactive proofs. And what it tells us about experiments. And I have to tell you, for me, this is really a somewhat disturbing idea. So this was inspired, by the way, by an argument that I had with Oded Goldreich and Madhu, which I'm in debt for. Arguments are really a good thing in order to make progress. I'm sorry? Well, what? So here's the thing. How does a physical experiment look like? The usual physical experiment is predict and compare. What does it mean? Well, here is an experimentalist doing an experiment, and he's testing a physical theory, and the theoretician, I forgot a theoretician. So a theoretician here needs to compute the prediction of this theory, and then they somehow need to compare their results. So that's the predict and compare paradigm. And every physical experiment works according to this. The only problem is that if we want to test quantum mechanics, this paradigm fails. Which part of it fails? Well, the presentation fails. Okay, the left part. I'm sorry? Yeah, Avi fails. So you cannot perform this calculation efficiently, assuming that BQP is not equal to BPP on a classical computer. You cannot make the prediction. So how can you perform the experiment? So that means that it's impossible, inherently, if you really believe that BQP is different than BPP, it's impossible to test many-body physical systems, quantum systems, in the predict and compare paradigm. So that's really disturbing because that's all we have done so far. So we haven't tested quantum mechanics in this high complexity regime where we cannot simulate it. Yes?
But out just means that there are out cases. It doesn't mean that every case is out.
Yeah, but these are the interesting cases. And that goes back to Madhu's question.
If a quantum computer factors an integer for you, you can check it. But suppose it solves some other problem that it does not have an efficient classical checking. How do you know it's right?
Yeah, we'll get to the factoring point in a moment. But this raises a very fundamental set of questions, like did we ever check quantum mechanics in the high complexity regime? Is it possible to test it? If we have an experiment going on, how do we test? Suppose people are trying to experimentally realize quantum computation of 30, 40 qubits. How do we test that what they have is really correctly evolving according to what they claim they have? Also, various questions in cryptography. How do you delegate a quantum computation without knowing what it should give you? So the alert listeners here already noticed that Shor's algorithm goes around this thing, and the way it goes around this thing, well, it does perform an experiment outside of this scientific paradigm, right? This usual predict and compare paradigm, it does test quantum mechanics beyond BPP. How come? What does it do? Well, the point is, if you look at it carefully, is that in fact, it performs an experiment which can be placed in the framework of an interactive proof. Shor's algorithm can be viewed as an interaction between a verifier and the quantum computer playing as a prover, and the prover gives the factors to the verifier, and the verifier can verify by some calculation. But it's not just a comparison. And this additional little step can actually be extended to a full interaction between the verifier and the quantum computer in order to actually create a paradigm of interactive experiments in which the verifier or the experimentalist modifies the experiment according to the different answers given by the computer. And this excess power of interaction buys you the ability to test all of quantum mechanics. Now, I had a slide explaining the power of interaction, but in fact, I don't think in this conference we need to explain the power of interaction. Just look at Avi's work, and that's the power of interaction. So verifying quantum evolutions is possible using interaction for BQP, entire BQP, not just Shor's algorithm. The way this is done is by error-correcting codes, but I'm told I have no time to even hint about it, so we'll go on. Okay, I just want to mention one question, which is, can the fact that such interactive proofs enable testing quantum mechanics actually raises the question of whether interactive experiments are useful in other places, in physics, in biology, in other places where you want to test things that you don't really understand. Yeah, question. There was a question. Okay, so one slide about quantum gravity. Quantum gravity is complicated, but fear not, Silvio, I predicted that Avi will be knighted today ahead of time. So we have Avi on our side, so we can enter a black hole. Over the past few years, there has been amazingly intriguing connections made between quantum information and black hole and quantum gravity. I have no time to tell you about quantum gravity in 30 seconds, but I just want to mention one thing. Quantum gravity is basically about connecting quantum and quantum evolution, which is unitary, and general relativity, which has within it, presumably, irreversible processes. So there are problems in combining the two, and one of the most successful, or the successful approach so far in order to try to combine them is called ADS-CFT correspondence, which is basically a correspondence between two physical theories, one in dimension d+1, in the bulk here inside this creature, and the other is on the boundary, a D theory. So this is a manifestation of the holographic principle, taking a theory in d+1 dimension and relating it to a theory in D dimension. And somehow this helps in explaining some of the paradoxes in this combination of quantum and general relativity. And how does quantum information get into the picture? Well, the very question is already talking about quantum information, but one particular connection that was made recently is in this understanding. So it turns out that if you want to represent an operator inside here, this is a cut of one slice here. And it turns out that this mapping between the two theories, the D and the D+1 theory, somehow enables one to take an operator in the bulk and represent it as in terms of operators on the boundary. And the thing is that in their description of these operators, it turns out that one operator has several different equivalent descriptions. One, say, supported by operators on this side of the boundary, and the other on this side of the boundary, on this part of the boundary. And this is exactly the characteristic of error-correcting codes, that you have the same operator having an equivalent description by using a completely different operator. For example, in the toric code, you can have something working on this loop and something working on the other loop. And since these loops are topologically equivalent, they're the same operator. And indeed, one can actually show that the ground space of CFT has the structure of an error-correcting code. I'll leave it at that. There are many, many different interesting connections here. And let me just say some concluding words. There is this issue of fear in science, right? There's a lot I think a lot of science is about psychology. And I'm not saying psychology is about science. A lot of science is about psychology. And especially, we're all afraid of various things, like will we ever do another important thing again? Will we manage to deliver this talk without people fainting? Will we manage, or without me fainting, will we manage to, whatever, all right? We encounter a lot of fears. Well, all of us, except Avi. Avi is not afraid of anything. Well, I want to tell you something which was very comforting for me. Avi is afraid of something. It's not anything related to science, but it is related to swings. So me and Einat and Avi went in '97, Einat was 12, to Six Flags. And Einat was 12, she really wanted to go on this little swing of 60 meters high. And we had to somehow, well, none of us really wanted to go on that swing, I have to tell you. I definitely didn't want, and to my surprise, Avi also didn't want, because he was afraid. And so we tossed a coin, and I lost. And I went on this swing, and I have to tell you, so I went off this swing. Avi told me, you never looked more happy in your life. And so I want to end this talk with thanking Avi for the even when you lose, and even when you're not on the swing, you are inspiring. So I want to tell you, thank you for the inspiration for me and for so many other people. Thanks.